First, okay. So first of all, I tell you what a Sasaki-Einstein manifold is. So let's start with a compact Riemannian manifold of odd dimension. So this is a real manifold, okay? And since it is odd dimensional, of course, it does not emit any complex structure. In particular, you cannot talk about Keller metrics on this guy. And what you do, you say that Mg is Sasakian if you take its cone. So the cone is, I don't know what to do, Cm. Well, this is just M times the positive real line as a manifold. And then you put a metric on this guy. And the metric is just, so the metric G, but you multiply with R squared. R is going to be the coordinate on the real numbers. Okay, so you take the metric, multiply by R squared, so this goes to 0 when you go 0 here. And on the other factor, you take, sorry, on this factor, you take just the Euclidean metric. Okay, so I denote it with dr squared. Okay. So you don't take the product metric on these two. On one factor, yes, this is just the Euclidean metric on R plus, and here you warp it with this R squared. This is called the conical metric. I mean, if you work a bit with metrics, you have seen this already. Otherwise, this is just a simple definition. And you say that Mg is Sasakian if this guy is Keller. Okay? So if this guy is Keller. So note that this have more than one requirement, right? This means that, okay, now this is even dimensional. So it means that this has a complex structure, first of all. This is already a requirement. Plus that it has a metric which is compatible with the complex structure and which make this Keller. Okay? So you think about this as the odd dimensional version of Keller manifolds. And then you say that Mg is Sasaki-Einstein. Well, okay, now this is obvious. Sasaki-Einstein. Einstein. If it is Sasakian, and Einstein. And G is Einstein. And G is Einstein. So this is the same as saying actually in this case that the Ricci curvature of G bar. So let's call this metric G bar is 0. Yeah. So you can also, but it's the same thing in this case. Is a little computation that the Ricci curvature is a multiple of G, right? Like always. So the Ricci of G is lambda G for some constant lambda. So these two now are equivalent. It doesn't need to be Calabi-Yau on the cone. Yeah. So for instance, okay, the easiest example is just it's just the sphere. So now with the Euclidean metric. So here it really means when I say S to n minus 1, this is really just the sphere in R to n with the induced metric. And this guy is Sasaki-Einstein. And the reason is just the cone of this guy you can do as an exercise is just C, is just the complex Cn minus the origin with the Keller-Einstein metric on Cn. Okay, so these are now I don't know where to put that. I think if I do this, then it's too low. So okay, so the study of these metrics it's mainly important in differential geometry and in string theory. But today, what I'm looking today is sort of a very explicit question. And today we are just looking at sphere. And I need to tell you what I mean with this. So a manifold sigma n. I try to stick with the notation sigma when I'm talking about homotopy sphere. So a real manifold of dimension n. Sigma is a homotopy sphere. This is the definition. Sphere if it is homotopy equivalent to the standard sphere. Okay. So I will denote the standard sphere with Sn. Okay. Yes.
Boundary condition. So then the example is not complete nature. So in general, what's the correct boundary condition for?
Though usually I'm assuming that M is M is compact, so there shouldn't be any problem.
The zero point.
Yeah, that's no, but
Zero and infinity to make it work whole. You don't need to do that.
no, I think it's no. I think it's okay like this. Yeah. So these are our guys. This is an old terminology, a classical terminology. Of course, by Poincaré conjectures, this just means that it's homeomorphic to Sn. Okay. Homeomorphic. But I will stick with the original terminology before the Poincaré conjecture were proven. Well, and I mean, there are real manifolds that are homomorphic to Sn, but they are not diffeomorphic, right? They are called exotic spheres. So I will talk much more about this later. So now we'll just say exotic sphere. So this is an homotopy sphere. Homotopy sphere. Which actually has a different differentiable structure than Sn, not diffeomorphic to Sn. And then the last definition I need, and then I'm essentially done. It's what it means to be parallelizable for a manifold. And it just means that the tangent bundle is trivial. Okay, so I'm going to write it in case a manifold is parallel. If its tangent bundle is trivial. Okay, so what do we know about Sasaki-Einstein metrics? Maybe let me go directly to, to this paper by Boyer, Galicchio, and Collar, so from 2005, and they proved that there exists Sasaki-Einstein metrics on any homotopy sphere of dimension for n plus 1. Remember, we're looking at odd dimension, and then we have two cases for n plus 1 or for n minus 1. And then the conjecture, sorry, no, this is not, the sentence is not finished. This is Sasaki-Einstein metric on any homotopy sphere that bounds a parallelizable manifold. So when you have a sphere, you can ask whether it is a boundary of another manifold that is parallelizable. This is the case for the standard sphere, right? Because the disk, the standard sphere is a boundary of the disk, and the disk is contractible, so the tangent boundary is trivial, so in particular is parallelizable. So the standard sphere bounds a parallelizable manifold. And then we are only looking today at this sort of spheres. This will be clear in a while why we're doing this. But is the statement clear?
Boundary cannot define your boundary. The boundary is not defined.
No, but it's okay. You see what I mean here with the sphere that is the boundary of the disk? That's what I mean. So,
boundary.
Yeah.
The number is not defined for any.
Okay. So this is the first paper really on the topic, the big paper. So okay, this is an Annals paper. Is a beautiful work, and we are going to follow the construction they use to construct this Sasaki-Einstein matrix, and I will explain the construction in 1 minute. But the second breakthrough is this Collins-Sekelidis. Actually, it's more efficient if I do something like this. I state here the conjecture. So in the same paper, they pose a conjecture, and they say that the same is true. Same holds for, let's say, in dimension for n minus 1. I forgot to say, this is a project, I wrote it down, but I wrote it down, but I didn't say it. So it's a paper together with Yu-Chen Liu and Taro Sano. Okay. So the second breakthrough on this topic is due to Collins-Sekelidis. Sorry, I need to spell it correctly. This is from 2019. And they proved that there exist actually infinitely many. There exist infinitely many Sasaki-Einstein matrix on the 5-dimensional sphere, okay, the standard sphere. And then they conjecture that this is true for any standard odd-dimensional sphere. Okay. So the big step is that they constructed finitely many metrics on the sphere, and here they were able to construct infinitely many. And okay, our theorem is that this all is true. So actually any homotopy sphere of dimension 2n minus 1 admits that bound parallelizable manifold that bound manifold admits infinitely many Sasaki-Einstein matrix. Okay. So here n you have to take at least 3, because if you take n2 you get the 3, but in dimension 3 there is only one sphere S3, and Sasakian 3 manifolds are classified. You don't get infinitely many. I mean, you get only up to diffeomorphism to deformation, you get only one. So here I wrote infinitely many. Hopefully, yes. I mean a bit, not just that they are not isometric, but actually they are also not deformation equivalent. So it's a bit stronger than. Okay, so these are the results. Any question about this? Okay, good. Okay, so I explain you the construction. So actually, I'm not sure that this is what people wanted. They were wondering if there were infinitely many, and there are, but I'm not sure that they are so happy about that. Yes, I will. Yeah, I'm going to parameterize them by integers. So yeah. Yeah, somehow it was very curious that they were here. They proved that there were actually more than one. And then somehow Colin Sikalides said, oh, look, actually on S5 there are infinitely many. And then, yeah. Assuming, yeah, I'm always assuming this condition. Okay, so let's see the construction. The construction is a classical construction. So take A naught, an plus 1. These are positive integers, okay? I think just an. So n plus 1 integers. Actually, I'm assuming them to be strictly bigger than 1. And then you take YA, this is the Briskon-Parm singularity. So this is just Z0 to the A0 plus Z1 to the A1 plus, so the Fermat equation in C n plus 1. This is called Briskon-Parm singularity. So we care about the origin, and this is the only singular point of this guy. And now there is a series of facts, essentially all proven by Milnor in the 60s. That tells you that if you consider the link of this singularity, I'm going to call it LA. So this is just YA, and you intersect with a small sphere. This is a real manifold, and is actually it's also compact. Is a smooth, compact, simply connected manifold, and it also bounds a parallelizable manifold. So this guy is going to be our sphere. It's not always a sphere. We need to study when it is a sphere, but at least it's simply connected and it bounds a parallel manifold. It actually bounds the Milnor fiber of this singularity. And you can prove that the Milnor fiber is parallelizable. But the Milnor fiber actually in this case is diffeomorphic to the same equation equal to 1. But okay, for us that's not relevant. Okay, so and I will actually show you later that in this way you can construct all possible homotopy spheres that bound parallelizable manifolds. In particular, all the exotic spheres with the condition that they bound a parallelizable manifold. Okay, so now how do we pass from this guy to something that we understand? And the trick is this. We take D, the least common multiple of the AI, and then DI is going to be D over AI. And there is, well, I'm going to write it here. So there is a sister action on YA. That is the usual one. So lambda Z naught Z1 is equal to lambda to the DI. So D naught Z naught lambda n dn Zn. Okay. And now if you take the quotient by this action, you get here the weighted projective space, P d naught dn. And on the other side, well, this of course is fixed, is invariant by this action. So you take the quotient, and this gives some weighted hypersurface here. But the equation is just the same. Is just the same equation in this weighted projective space. So this is a weighted hypersurfaces. I'm looking at it as an orbifold. Okay, so it's a singular guy, and locally is just the quotient of Cn by a finite group. Okay. So this orb, just remember me that it is an orbifold. And now the theorem. This is Boyer-Galicki in 2001. They proved that this link LA admits a Sasaki-Einstein metric if and only if this X orb admits a Keller-Einstein metric. A Fano Keller-Einstein metric. A Fano Keller-Einstein metric. So the lambda in the definition of Keller-Einstein metric is negative. I mean, otherwise said that this guy is a Fano variety and it emits a Keller-Einstein metric. Okay. Now, see, this is good because now we have, well, this is a complex manifold, so we can treat it in some way. The theorem the proof is not particularly hard, but there is some work to do, and is really doing with the fact that the link is as S1 bundle over this guy, and they can lift the metric from XORB or descend it from LA. Okay, so now we have something to prove in complex geometry, and somehow the main point is that we give a criterion. Okay, so see. Okay, just order your AI En, then XORBs admits a Fano Keller-Einstein matrix if and only if one is less than the sum of the 1 over AI. And this must be less than 1 plus n over the biggest weight. So this is our criterion. And I should be a little bit more precise. This is, of course, a Keller-Einstein metric on a singular, so it's an orbifold Keller-Einstein metric to be preferred. But this is exactly what you have in mind. I mean, yes. Okay, so this is a numerical criterion, and you see if you write down these numbers now, and they satisfy this condition, these two conditions, then actually you know that the link has a Sasaki-Einstein metric. Okay? Because of this theorem here. Maybe it's important to say that this was known to be necessary. So the condition was known to be this is called Lisner-Ovis obstruction to the existence of Keller-Einstein metric. And this was proved by, okay, I'm just going to write the letter, sorry, Gauntlet, Martelli, Sparks, and Yau in 2007. So what we actually have to prove is the other direction. Yep.
So this particle must have a Ricci particle 0, right?
No, this is going to have a Ricci curvature that is going to be negative, right? Okay.
How far away the problem came in from the angle this mentioned? From where to project?
Yeah, so actually that's a good point. So this first part just tells you that that X is Fano. So I can write it down. So let me maybe sketch the proof. So so you see X orb. Okay. It's easy to write down the canonical divisor of a weighted complete intersection. This is just O, and you take the degree D minus the sum of the weights, right? And this is negative, so is anti-ample. Yeah, if and only if. This is negative, and you divide by D, and you get exactly this condition. Okay, so this is trivial. Okay, so now we need to prove that if it emits a Kähler-Einstein metric, then it satisfies this condition here. So this is our goal. Okay, how much do I say? Well, I can explain a bit. So the proof goes like this. So to any orbifold, like this one, you have a pair X delta associated to it, and the construction is sort of the following: the orbifold is locally a quotient, and so it's going to branch on some divisor. So you consider the branch of the divisor and the index of ramification, and you can construct a pair. This is going to be a divisor. But in this case, it's very explicit. So actually, I tell you what the pair is. So we can write down sort of the equation. And the problem here for people that works with weighted, that know some stuff about weighted projective spaces, is that this guy is not going to be well formed. So the first thing we do is just to make it well formed. And this is a standard thing you do. You take the greatest common divisor of all the weights except one. So a weighted projective space is called well formed if every time you take away one weight, the remaining one has no common factor. Okay, so this takes care of this problem. And then you define A prime as AI divided by GI, and then you take as G the product of this GI. And then our X is going to be Z naught to the A naught prime plus Zn to the A naught prime Z inside dn gn over G. So this is just a simple trick to make this weighted projective space well formed. So this is X is sorry, equal to 0. So it's a weighted hypersurface in this weighted projective space. Let me call this weighted projective space P prime. And then the boundary delta is given by 1 minus 1 over Gj Hj, where Hj are just the hyperplane. Intersecting with X. So this is we get in this way we get the variety and our divisor. And the point, and this is again a theorem. Somehow in this form, the theorem has been proved in a paper by Collins and Sekelidis. It says that the orbifold admits Fano-Kähler-Einstein matrix if and only if X delta is K-Pauli stable. So what's the point? To construct Kähler-Einstein matrix is actually very hard. That's the reason why in the 2000s, they couldn't really construct so many Kähler-Einstein metrics. But nowadays, we have the notion of K-stability. This is the algebraic analog of Kähler-Einstein matrix. So this is just one, this is somehow Yau-Tian-Donaldson conjecture for cones. So Chen-Donaldson soon proved the Yau-Tian-Donaldson conjecture. They say that for smooth manifold, the existence of Kähler-Einstein matrix is the same as the K-Pauli stability. And then Collins-Sekelidis, somehow following the same proof, they prove it for this sort of guys here. And now we are happy because this is an algebraic geometry condition. Okay, so it's much it's easier to deal with. Okay, so we have now how do we prove that our pair is K-Pauli stable? And yeah. Please.
For manifold, not orbifold. We have a test for the stable and same thing as the Kähler-Einstein kind of thing.
It's very hard. Very hard to prove. Yeah. Also for smooth case. Yeah. So I should say that one direction is due to Berman, and the other direction is due by Chen, Donaldson, and Sun. Chen, Donaldson, Sun are 3 papers, 2 on jumps, and Berman is an inventionist paper. So yeah, definitely hard stuff. But we're just using it, so we're not proving it. Luckily, Okay. Now let's prove that X delta is K-Pauli stable. And this is a bit of a trick here. This is just the standard projective space of dimension n. This pi prime is our weighted projective space, and there is this Galois cover. That sends you a point there to the powers of. Yeah, fine. Now it's easy to check. Then our x lives here, and this guy is just the pullback of KL plus the sum of 1 minus Li, where now L is just in this projective space is just a linear subspace. So it's a very simple observation, right? This equation here, in these new variables become just this equation, okay? And the Li are the corresponding hyperplane. So W equal to 0. Something with that. Okay, so this is a simple observation, but it helps a lot because now there are results that tell you that X delta is K-Pauli stable. If and only if the pair downstairs, so L and this guy here, is K-Pauli stable. This again is non-trivial. I should write a name. There are at least two proofs, Liu Zhu and Zhuang. There's each one. This is one nice feature of K-stability, for instance. It behaves well via finite morphism. So maybe, I don't know, here is K-Pauli stable. I don't know how much you know about K-stability, but somehow, well, K-stability is that some K-semistability is some invariant. The Nelson-Futaki invariant is at least 0. K-Pauli stability is that when it's 0, if and only if the family you're considering is trivial. So and if you are K-Pauli stable and your group of automorphism is finite, you are K-stable. Okay, so this is the way it fits into the stability. Okay, and then you have to do some computations, and essentially it's you use some result of Kento Fujita. Use some result. So more precisely, he has a paper on K-stability of hyperplane arrangements, and this is exactly the situation in which we are. So he writes down exact condition on these coefficients, and you just check they are the same as the one in the theorem. And you check that, yeah. Okay. Does it make sense? Okay, so this was the sketch of the proof. And now I think I'm going to talk a bit about homotopy spheres. So this part here, it's really classical, and essentially it goes back to Kever and Milnor in the 60s. And they showed that if you consider the set of sphere that are homeomorphic or homotopy equivalent. Sorry, the manifold that are some homotopy sphere of dimension 2n minus 1. So these are manifold. I gave the definition before. These are manifold that are homomorphic to the standard sphere, and you mod out by oriented cobordism. This is the same H cobordism. This is the same actually as modding out by diffeomorphism, okay, because of Smale's theorem. So let's assume maybe, okay, let's do it this simple. Let's assume that maybe n is at least 3. So by Smale's theorem, this is the same as oriented diffeomorphism. Oriented diffeomorphism. This is Smale H cobordism theorem. So these are the objects we care about. This is sorry, what's the point? This is a finite group. So this is a finite group. Is a finite group. And the operation is the connected sum, and the standard sphere is the trivial element. And the spheres we are looking at, which are denoted by B, P2N, these are the guys that bound, so classes of sphere that bound parallelizable manifolds the 2n is because they bound a manifold of dimension 2n, and the B is for boundary. This is a subgroup, is a cyclic subgroup. Is a cyclic subgroup. Okay, let me tell you some more about if n. So these spheres have dimension 2n minus 1. If n is odd, then this object here, the subgroup we are looking at, is either 0 or Z2. Is 0 or Z2. So this means that in dimension 4m plus 1, you actually have only the standard sphere and possibly an exotic sphere. Okay, that bounds parallelizable manifold. I think it's still not known in general which one of the two is. It's still an open problem. And if n is even, and you get a lot of exotic spheres. If n is even, then the order of this group for m is 2 to the 2m minus 2. Okay, it doesn't matter for us the exact number, of course, but just to give you an idea. It's not is of this order, I mean. So there are a lot of them. Maybe 2 examples. So in well, in dimension 5 there is nothing, right? So there is no exotic sphere. There is only one sphere. In dimension 7, there are 28 of them, and all spheres in dimension 7 bound parallelizable manifold. In higher dimension, this is not true. So it's, in some cases, this is really a proper subgroup. Yes. No, it's not easy. Yeah, I cannot. Yeah. Yeah, it's some characteristic computation, I think. Yeah. Yeah. So the exact number, but it doesn't tell me much. So, but I can write it to you. Here you have to put the numerator of this fraction. I wrote it somewhere. So you take the numerator of 4bm over m, and bm is the mth Bernoulli number. But okay, to me, it doesn't say much. So this grow very quickly, like BP16 is already 8,000 and BP20 is already 130,000. Okay. Yeah, this is a beautiful theory that they worked out. It's really amazing. Okay, so recall what is our situation. So what are we looking at? We are looking at the following guy. We have this Briskon-Pam singularity, way YA. So this was this guy. And then we called LA its link. Okay. And now I wrote down before an exact criterion to decide whether the link admits a Sasaki-Einstein metric. Now the point is to decide when the link is a sphere and which sphere it is. And there is a theorem by Briskon. Well, actually, wait, let me introduce first a graph. So you consider the graph. Okay, so GA is a graph with n+1 vertices. n+1 vertices labeled with this AI. And two vertices, so AI and AJ, are connected. I different from J. If they have a common factor, if they are not coprime. Okay, so the greatest common divisor is bigger than 1. So this gives you a graph. And then there are criteria to decide using this graph when a link is a sphere. I'm only telling you one. So let's do this one. So if GA contains at least two isolated vertices, then our link is a sphere. So it's homomorphic to a sphere. It's a homotopy sphere. Yeah, this is enough for what I want to do, I think. Okay, so now we also have a criterion to decide whether it's a sphere. But now I told you the main theorem is that we construct Sasaki-Einstein metric for any spheres that bound a parallelizable manifold. So we need to understand this group is huge. So we need to show that for any element of this group, we have infinitely many Sasaki-Einstein metrics. So we need to decide also what this tell you the homomorphic type. You need to decide also the diffeomorphism type to distinguish between them, right?
And I know, so is the negative component two is not good enough. This what's the partial result about the component is bigger than two?
Contain the graph, just the graph, yeah.
What isolated point? I must in at least two connected components. So any relation between these two kind of statements, Jones?
No, not that I know. I know that there is another criterion, but no, it's not on the side yet. Okay, so good. Now let's look. I'm going to do this case. So N is going to be, I'm going to do the even case, which is the interesting one, right? Is the one in which we have a lot of exotic spheres. And I want to explain you how to construct the matrix. So first of all, assume that our link is a homotopy sphere that bounds a parallelizable manifold. For instance, if we satisfy this criterion, it is. So it's an element of this BP4M group. Then the diffeomorphism type, of LA is determined is it here? So it's determined by 1/8 tau. I'm gonna write it tau A. This is going to be an integer. You take mod the order of our subgroup, where tau A. So okay, is the Hirzebruch signature on the H2 of the Milnor fiber. So it's the Hirzebruch signature. Now, this wouldn't be much useful written like this, but the point is that these people, Briscorn and the others, show that there is actually a combinatoric formula for tau A. Since I still have half an hour, I have half an hour, right? Yeah, it's 1 hour and a half. Okay. I'm going to write down the formula just for fun. So you have to count the point in Zn plus 1. Sorry, yeah. Well, let's write 2m plus 1. It's the same. In 2m plus 1, such that the coordinate of the point x, they are all between 0 and ai, and this expression xi over ai is less than 1 if you consider it mod 2. So you can take away multiple of 2 from this number here. So this sum goes from 0 to from 1. Okay, no, from 0 to 2m. This is correct now. And then you do minus, and you take the point. In 2m plus 1. Always with coordinate between 0 and ai. And now you count the same sum, but you count the one between 1 and 2. 1 and 2. So it's again is not so explicit like the other criterion I wrote down, but it's combinatoric expression. And now, for instance, in this way, you can construct all exotic spheres that bound parallelizable manifold. I will show you. This is not our construction. This is Briscorn stuff. And you just take A to be equal to 2. 2. So all 2, then a 3, and then a 6k plus or minus 1, doesn't matter. So this is our element in 2m plus 1. And then we know by the general theory that, no, sorry, we know by this result here. You see these two. Sorry, k is any integer. You can. And now by this result here, this guy is an homotopy sphere, right? Because these two vertices are isolated. So it belongs to our group. And then you can actually compute this number. It's going to take maybe, I don't know, maybe 15 minutes, but you can really do it by hand. You do it and you get -1 to the m -1 to the mk. So in particular, if you vary k, you get all the possible spheres. Yeah.
So,
It's not helpful for this talk. No, no. But it's just the signature on the H2 of the sphere of the Milnor fiber with the intersection form you get from the yeah. Yeah, it's because that's the if you try to put one of the two, then it's not correct. Yeah, it's funny. Yeah, it's funny. Yeah. Yeah, so you can check this. So let me write down actually what it means. So we get all possible elements in BP4M. So all possible homotopic sphere that bounds parallelizable manifold. Okay, so now remember that our link admits a Sasaki-Einstein metric if and only if this is the theorem I wrote down before. So the sum of the reciprocal is bigger than 1 and is less than 1 plus n over an. So if you use this sphere, this doesn't hold, right? There are too many 2's. This sum is going to be too big. But you can correct it. So let me finally write down the examples. Take k, well, any integer, but somehow let's just make it vary in between 1 and then the order of the group. Then we take the first two, A0 and A1 equal to 2. Then all the other up to n minus 1, sorry, n minus 2, they are equal to a number p that I will tell you what it is. Then an minus 1 is going to be p plus 1, and an is going to be p plus l, where so l is just let me take 6k minus 1, like in Briscoe construction. This p plus 1 you see correspond essentially to these 3. And then I have to tell you what p is, and p is just any positive number which is equal to 2 mod. You need to take a couple of stuff. I will explain why. Mod ml l minus 1 multiplied by the order of the group. So this p also you see correspond essentially to these 2, but now is mod by a lot of stuff. I will tell you. I mean, I don't think I will tell you much, but just the idea why. So, okay, so these are our examples. So you take the link of with A equal to this, and let's see what we get. Okay, first of all, note that if you take P now big enough, if you take P big enough, then this number satisfies this inequality. So L, sorry, I write AP is somehow this A here, okay? It depends on P. I don't know, maybe I could write something like this also. Or just A. And we know that it depends on P on L. So for P big enough, LA so admits a Sasaki-Einstein metric. Then it has two isolated points. So also it is a homotopy sphere. So also it belongs to this group. So it's an homotopy sphere that bounds a polarizable manifold. Now, now I need to tell you what this number is. And the way, the way we do it, there could be different ways, that we prove that tau AP is a polynomial. Sorry, tau A is a polynomial in P. In particular, if you think a little bit about it, since if you take P equal to 2, you get this number, then this means that you get always this number. Because of our choice of P, because you're killing a lot of stuff taking P mod that. So we get all spheres. So if you fix K, you get any sphere you want. And now if you vary P, you get infinitely many Sasaki-Einstein metric. You need to prove that they are different, okay? But this is possible. There is also a combinatorial way to do that. So varying P, you get infinitely many. Varying K, you get different spheres. Now, the proof of this proposition, it's pretty long, but it's sort of elementary. And maybe I want to say just 2 words. Or maybe I'm going to cut it very short. So, yeah, let me try to write a sentence. One reduces the problem to show that for any integer eta between 1 and n-1, the number beta eta. So this is the numbers of lattice point such that they are non-negative coefficient and the sum are less than eta. So it's not hard somehow to, okay, now the formula of tau is not there, but it's not hard from the formula of tau to go to such a formula. And this one, now why I want to write this down, because now this is, what does beta eta count? Beta eta counts lattice points in a simplex, in the simplex of vertices or 0 and then eta A1 or 0. Okay, I know. This you can think about it. Eta AN. So essentially, we reduce the problem to counting lattice points in rational polytopes. This is also a classical topic in geometry. There is all the theory of the error polynomial. And I'm passing through that. You can show that this guy is a polynomial in P, which is what we want. Yeah, okay. I think I'm actually said all what I wanted to say.
Okay, thank you, Luca. So anyone has any questions or comments?
Can I ask a question? Can you hear me?
Yes.
Yes.
So I try to understand the condition in your main theorem. Now, suppose a homotopy sphere does have a Sasaki-Einstein metric. Does it mean that it bounds a parallelizable manifold?
Yeah. So all the links coming from Brice-Comparme singularity, they bound parallelizable manifold.
Okay.
This is a theorem of Milnor.
Ah.
Okay. So, and we are only looking, all these links, they all come from this Brice-Comparme singularity. So automatically they bound parallelizable manifold, even if they are not spheres.
Okay.
Okay. Of course, it would be interesting to say something in the case in which you have for the other spheres, but I think no one has an idea how to construct the other spheres in an efficient way. Like this is a very nice way to construct the ones that bound parallelizable manifolds.
So if it is a sphere, it doesn't mean that what is inside is a ball, right?
No, it does not mean that. No. There are spheres. Now I cannot write down an example now, but there are homotopy spheres for which the interior is not a disk. Somehow is not parallelizable.
Okay.
So. But
in your case, where there is a Sasaki-Einstein method,
yeah, in all these cases, it's okay.
Not necessarily a ball. Is it correct?
Yeah, a ball. I mean, yeah.
Okay.
Yeah.
Thank you.
And already got a condition.
Oh, I think the two isolated vertices are. Oh, you mean not in this example, in general? Sorry. Oh yeah, that's a good question, but I'm sorry, I never checked the proof of Brice-Cornier. So.
Kinetic component bigger than 3, no good enough one. Just as more nature and more geometry.
Yeah, there must be also a geometric reason, but yeah, I'm sorry, this I don't know.
You already have infinite limit, countable infinite limit metrics on the sphere. So can there be more? Alternatively, if we think about the modular space of these metrics, do we know the dimension of that. So if that's 0, then this is the best we can get. But if it's greater than 0, strictly greater than 0, then we should have like uncountably many metrics on the sphere. Do we know whether anything has been done on that or not?
Yeah, that's a good question. So okay, but
Yeah, because
oh, you see, this belongs. This I didn't explain at all. But actually, we can prove that these guys belongs to different component of the moduli spaces because they are not deformation equivalent. So actually, you have infinitely many components in the moduli spaces. Yeah. Yeah.
Any other questions?
So if there doesn't exist an SC metric, can anything be said sort of like a optimal destabilizing type of statement or a convex minimizer kind of thing? Does that sort of work?
I mean, in the case, for instance, in which, so in the case in which there
in
is
the
no,
unstable case, I guess.
no, I don't know that. I never thought about that. That would be nice to see some that should correspond to some unstable Kähler-Einstein metric. So yeah, but yeah, I don't know.
Any other questions? Comments? If no, then let's thank Luca again.